Okay, well, I'm Jim Maltby. I'm honored to be the first outside speaker to use this beautiful new room. The last time I spoke here, almost exactly a year ago, I introduced myself as coming from Cray and as an application specialist. Cray is very excited about the possibilities of big data, and so we've actually created a new division called YARK Data. And many of you probably are wondering, where did we get such a silly name? And in fact, YARK is Cray spelled backwards. And it wasn't taken. That's one of the problems with, in the high-tech world, most of the good names are taken. There's also an internal Cray joke that we actually have a chip called YARK, yet another router chip. And so it's actually named after a router chip. Okay, so I'll be giving you an introduction to what Cray is doing in big data, how it relates to the XMT2, and then a new big data appliance that we call uRiKA, that is a software layer built over the XMT2, and which I will describe in great detail. And of course, there are also questions: what is uRiKA? Here in small print, Universal RDF Integration Knowledge Appliance. Knowledge appliance is very important. RDF is a technology which some of you are familiar with, I know. I'll explain that in more detail. Okay, so I'll start off with Cray's motivation for making such a large effort in this field. We believe it's very important. So I'll talk about big data analysis and why we built uRiKA. And then I'll do a quick overview of the XMT2. We'll get more technical detail about the XMT2 in some of the later talks. But then I'll get to the description of the graph analytics appliance, uRiKA. Next, I'll be talking about some customer use cases. I actually selected 3 pretty much at random, and I did not select one of the life sciences use cases. That's actually a very important field to us, and as a matter of fact, I'm working on a life sciences use case when I'm not here, but I didn't bring slides on that. Sorry about that, but I'll be glad to discuss that with you between the talks and tomorrow. Show some early performance results, and then summary. Okay. Basically, Cray thinks that this field is very important, and this is why. I guess CSCS thinks it's important too, since they built a facility to work with big data. But if you look at the growth of all the different types of unstructured data, semi-structured data, it's actually growing faster than Moore's Law. You all know about social network data, but there's quite a few other things in the life sciences field, banking, et cetera, where there's basically too much data for people to analyze well. So here's our definition of structured, semi-structured, and unstructured. Structured is traditional relational databases, spreadsheets, and things. Semi-structured are things like XML. And then most of it, the biggest thing, is basically what inhabits the web. Email, documents, multimedia things, things like that. And many of you here are probably not interested in analyzing other people's emails, but you might be interested in unstructured data like PubMed or Medline or the literature, things like that. So there's a lot of rich sources of unstructured data, and we hope to use that as raw material for our analysis. And so basically, volume goes without saying, certainly from the graph. Variety, I'll touch on this later. Integrating data of different types is a real strength of semantic graph databases. And then finally, velocity. You just need a supercomputer to do it. And that's why we got in. Okay. I'm sorry for the buzzwords, but this is important. There has been a big change. Web 2.0, you all know about, basically working with document search. Web 3.0 generally refers to RDF, Sparkle, and the W3C standards, which I'll talk about. But it's basically graph structured data that exists all over the data, all over the World Wide Web, and can be analyzed in a much deeper way. It's interesting, and when I made this slide, Google was in the Web 2.0 box, but just last week they announced their new knowledge graph, which is based on Freebase. So they've thrown their hat in the ring now, so they're interested in a graph approach to big data, though they are the archetypal Web 2.0 company. So, as I mentioned before, allows you to merge different data sources, do pattern matching on complex queries, and acquire deeper understanding to your data. Okay, this is the healthcare. This is an example from the healthcare industry. I have some more information on that later. Imagine you had a general question like, what drugs are causing post-op addictions in hip surgery patients? Well, you need evidence from many different sources. So there are the health records from the hospital. Go to a drug taxonomy to understand what different drugs are out there, what they might be involved with, what effects they have. And then finally, go to a database of psychiatric disorders and results of all of these things. So you can put together a complex pattern that describes what might be happening, but it uses 3 different data sources that you're trying to integrate together, and it also is a very complex pattern. This is a pattern that's not expressible as a simple table, and it's not in general domain decomposable because there are cross-links between all of these different databases. So this query is easily expressed as a pattern, a graph-style pattern, but virtually impossible with keyword search. It can be done with SQL, but you need to reconfigure your database every time you change the query. So we believe that graph databases are the best way of solving problems of this sort. Okay, so in the field of big data, we have a definite niche. We're not the whole thing. The traditional big data approach is structured data, basically relational databases. It's a 30-year-old technology. Everyone has a database, as far as I know. So it works well with structured data. OLAP cubes, which, if you don't know what they are basically a very regular data structure. A good example of that is the Oracle Exadata machine. Very high-performance machine, very expensive. And this is a very useful technology. This is most of the big data field right now. A newer portion of big data is scale-out analytics. It's also known as horizontally scaled data analysis. This is where you do a lot of your social network analysis. You can build, this basically works very well on white box clusters. Doesn't need much of a interconnect network because these data sets by definition are quite partitionable. So you can break it up into a bunch of different pieces, throw it on a large number of white box machines with gigabit Ethernet, and work across it. So Hadoop and MapReduce are the 2 best known examples of that. And this, once again, is a very fast growing and very useful field. Now, the one that Yark Data is specializing in is in-memory analytics. So we're working with all 3 types of data. We're specializing in non-partitionable data. This is data that needs to be analyzed all in one piece. When you're traversing these graphs, you are jumping around from one corner of the database to the other, and so it's not in general partitionable. And also, we built a machine that does a very good job with pattern matching, and that's based on the architecture of the XMT, which we'll talk about later, of course. So in terms of a large-scale, scalable in-memory analytics engine, we believe we have this one is the best. And of course, CSCS has one too, yes? Yes, those would be exactly the same thing, yeah. And you can certainly partition any data set arbitrarily, but it's, if the data set lacks locality, then you'll be constantly jumping between your different things. And I guess I should point out that any of these three machine types, your Hadoop clusters, your Oracle Exadatas, can analyze this data, just very slowly.
The other thing is very fast. How do you change the unstructured data? For example, XML is unstructured data. I think XML is quite structured. How do you distinguish between structured and unstructured?
Oh, and I suppose there are XML databases. I guess when I think of structured, I think of something that is automatically arranged in terms of tables. It basically possesses a high degree of internal structure. XML is self-defining, and there are XML-based databases, so that's semi-structured. And then unstructured is, say, emails, publications, things like that.
Different format that it can be so structured that you can put everything together to try to write it.
Yeah, so absolutely, and I think I have a slide coming up on RDF in a moment. Okay, so that's basically why we're going into big data analysis. Are there any more questions on that before I go into the XMT2? Okay, so you're all aware about Cray's involvement in the supercomputer field. Many of you actually own very, very large Crays. And so traditionally we've worked in scientific computing. And so grand challenges. And this picture of what was once, several years back, the world's largest computer. It's the Jaguar machine at Oak Ridge. It's an XT5. And certainly, this is a somewhat older slide, showing some of the early records set with it. One of the reasons that I put this up here is because the XMT2 is based on the XT5 infrastructure. So the XMT2 is in fact a world-class supercomputer built with world-class technology. It just has a different processor. All the rest of it is the same. So it comes from a good lineage. Okay. Now, here I'm trying to explain the difference between sort of algorithms you would do on an XT5 or an XE6 and what you might want to do on an XMT2. So got a lot of experience in the room on how to achieve high performance on these large distributed memory machines. You need to place data near the computation. You have to have as much data reuse as you can. You have to load balance, decide how there's partitioning the data, and there's also partitioning the work. Minimize synchronization across the machine, which can be expensive. Avoid modifying shared data, and avoid adaptive and dynamic computations where you're jumping around the different distributed portions of the memory. But some algorithms, graph algorithms perhaps, can't take advantage of those techniques. So there was a question about data locality earlier. That wasn't a plant in the audience. The machine works well with data sets with very little locality. That break cache, for example. And also applications with a large amount of parallelism. Yes?
What about
Like transactional databases, for example?
about the applications of
Oh. Well,
for example,
mm-hmm.
we use bandwidth of
Mm-hmm.
possible to run
Yes, actually some of the most successful Graph 500 winners have have made use of good data aggregation things. And if the graph analytic problem that you're working on will work well with that sort of aggregation, then you can do very well. And as I say, the current winners of the Graph 500 have done that. It depends on how often you are jumping around data and the complexity of the graph analysis problem that you have. So I certainly agree that it's possible to program around it on a distributed memory machine, depending on your problem.
It's very interesting for the human brain network. There are different levels of sending different small packages. There's the different protocol in the system speaker, so it's not always the fact that any big message in effect will be more beneficial. It sounds like it's just it's really application-based dependent.
Yeah.
It's like what you try to expect from this.
Yeah, John, you had a comment? Okay, so basically, thanks, John, I appreciate that. I need a machine that can efficiently reference a large global shared memory and also tolerate long memory latencies. We haven't repealed the laws of physics. It still takes a while to get from one end of the machine to the other. So you need to be able to tolerate these memory latencies. And that was basically what motivated the design of the XMT. So I guess some of this will be repetition to those of you who already know the XMT, but it's basically a very large globally shared memory. Architecture supports up to 512 terabytes. Typically, we tend to ship 2 to 32 terabytes. Did I say megabytes? I meant terabytes. And so you can support sparse references across the entire memory of the system, the entire shared memory of the system, and it's highly scalable. It's massively multi-threaded. I'll describe the architecture of the processor later, but this is used both for parallelism in your algorithm and also for tolerating the global latencies of going across the machine. We have support for single word access and synchronization on a memory word by memory word basis, which is very important for supporting that large degree of parallelism. And then the software is actually a very important part of it. We have a very sophisticated runtime that automatically handles, in conjunction with the compiler, the parallelism in your algorithm. So it automatically does the thread management and load balancing. And so that solves some of the problems you'd ordinarily run into with such a high degree of parallelism. Any questions on the XMT? As I say, some of you already know about the architecture. I'll be going into it in a little more detail later. So basically, you don't need to worry about data layout. Data strides, that's more of a vectorization thing, but it's true of some modern processors. No partitioning, and you need to worry about synchronization, but we have a lot of support for that. So basically, it's very good for graph algorithms and sparse methods, dynamic methods. Data flow, I think John will be talking about a little bit later on. Okay, here's a little history of the XMT architecture. I was going to hassle John earlier when he said he'd been working on the XMT since 1997. It was actually called the MTA-1 back then. Our very first machine was launched in 1998 at San Diego Supercomputing Centre. Very complex machine, but similar architecture. MTA-2 was launched in 2002, reduced the number of chips and moved to CMOS technology. We sold several large MTA2s, but it was a very expensive board to manufacture because of relatively low density. The original XMT was launched in 2008, and it's reduced to a single chip that fits in an Opteron socket, and worked on the Cray XT3 technology, making use of all of their packaging, cooling, and RAS. So basically it's when we put the MTA architecture in a Opteron socket and implemented it in our big supercomputer hardware that the XMT really became a practical machine. And I'm proud to say that the XMT2 is an upgraded chip with some more features using XT5 technology. And the very first next generation XMT2 was delivered here to CSCS in 2011. So the last time I was here, we were here to celebrate the launch of the very first XMT2. Okay, now switch gears a little bit. If you all understand the XMT2, let me go into the Eureka Appliance. See, our motivation behind this was that there are many problems out there that are based on graphs, and that's the motivation behind the XMT2. We'd like to make it easier for people to work on that. And basically, in the database world, there isn't very good support for graph analytics. There's, when I say big data, I'm thinking of pretty much the database world as opposed to the supercomputer world. And that's an important thing to understand about Eureka and the New York Data Division, is that we're trying to expand out beyond ordinary supercomputing into a lot of problems that might arise in healthcare or in financial services industry or airline reservation systems, things like that. So we'd like to make this thing look more like a traditional database, but with the high-performance features built into the XMT2. So there are many other approaches to big data, but unfortunately they do not scale very well. Basically, there's all the Hadoop-style things, NoSQL, column-oriented, document stores, key-value stores. There are some in-memory relational databases out there. I think there's a new in-memory column store that was just announced last week. But basically, none of these scale well on complex graph-oriented queries. And this is why. Basically, graph-based data is difficult to partition. There's a question about that earlier, but if your graph spans all of the nodes and is relatively dense, you end up hitting high communication costs jumping around. So that strains the network. Graphs are not predictable. They're basically not predictable to a memory controller. When your memory access patterns are highly data dependent, this often blows cache. So it prevents usually memory is used to, or cache type systems are used to make up for the difference in speed between memory and the processor. And then finally, graphs are highly dynamic. You'll have new types of data streaming in all the time. So you'll be needing to load new data sets, update your data sets. And one of the things that supercomputers, particularly Crays, are good at is high-performance I/O. So this is why we took advantage of the strengths of the XMT2 to build the Eureka Appliance. We make use of the very large shared memory. It's a complete in-memory store. So you don't need to even think about partitioning it. The XMT architecture enables you to avoid caching. So you can jump all around anywhere in the entire database whenever you like. And then once again, we have highly scalable I/O. So this is just a cartoon of the ThreadStorm processor, and we'll describe that more in detail. So just to try to explain this is a picture of our software stack, sort of a picture of the architecture. At the center, we have the shared memory multi-threaded scalable I/O graph appliance, which is a long term for the XMT2 with a custom query engine built on it. So this is all proprietary, and it is written for the ThreadStorm processors. However, outside of that, the next software layer up is standard SUSE Linux, as you'll find in the front end of the XMT and the front end of all the other Cray supercomputers. So atop of the SUSE Linux, we have a graph analytics layer, which is based on something called Jenna. Jenna is a semantic database which was originally developed by Hewlett-Packard. They foolishly decided not to go into the semantic database business, and so they open sourced the Jenna database. And it has grown to actually kind of represent the standard in semantic databases. It's sort of the reference database for the Sparkle language. And so to the outside world, the Eureka Appliance looks like Jenna. So anything that you write to Jenna will automatically work on the Eureka Appliance, just far, far faster. Top of that, we've got an app visualization layer, which we're constantly trying to grow. And then above that, we're working in various verticals, trying to put together use cases and find out what software works. Everyone has their own favorite tools to work with databases. So, and some of them are listed here across the top. And the idea is that we're trying to be able to use all of this existing industry knowledge to get at the power of the XMT2 for problems of this type. And so there you really have the entire motivation behind this effort, and it's I think one of Cray's largest internal efforts. We believe that in making it easy to use all of the tools that people are using now in the database world to make use of this computer power is going to be a big win for us. And as I say, anything that's built there can be run on other platforms. It'll just run a lot faster on ours. So that'll be good for development, things like that. We're also changing our pricing model. These are leased, actually, rather than sold. So that means that you have less capital cost up front and more operational cost. Now, I'm just a scientist. I have no idea why that's important, but our business people do certainly believe that it is. Okay, so are there any questions on the, that's basically my first introduction to what the Eureka Appliance is. Do we have any? Yeah. Right. In the talk right after lunch, I'll go through the whole workflow, how I suggest that people will make the best use of this appliance. But the idea is that people are supposed to use the Eureka Appliance and the semantic database, that you will use the tools you're used to, say Java or relational database things, and that you never have to program in C++ at all. And as you know, the XMT, and there'll be more talk about this too, the XMT is C++, but it has additional pragmas and there's additional programming considerations. So the central point is that we want people to be able to use that power without actually having to program the XMT2 core. Yeah, no, we do think that's a good idea. Yeah.
Without question, probably it's not the right point now, but anyway, how does the accounting work in that case? That's not job-based, right?
How does what?
Accounting.
Accounting.
This user,
Oh, you mean actually job accounting on the machine?
Yeah, yeah. So if you are default to require the CPU time, for example, spent by CPU, or that's not appropriate for this.
Oh, okay. You know, I know where you would do it, but I don't know what. I mean, anything like that would be done through Jenna, where it has all of the necessary information. So it would be, you know, I actually hadn't thought of it.
Okay, but you could require some external account for it.
Yes.
Stored it in the
Right. We do have, we have all that information, but right now we're not doing anything with it. So that's a very good question, actually.
Write it down to my
Okay, I'll write it down and do this. Any other questions?
You can ask, well, secrecy from what they try to do with our activity. Maybe they have some idea.
Yeah, sure. But that was my question. What should I ask for? Like for computation time or like for data space or how can I do it like say how it should be?
Because it's quite different from for the XQCs or whatever.
Yeah.
This
Yes.
is another philosophy.
Oh, I'm sorry.
This is a question related to account.
Uh-huh.
In the
Uh-huh.
you support somewhere protection domain for different zones in the same node.
That's right.
So, is there any reason to run different applications on the same node and not to work with partition applications?
Right.
Protection, they can benefit from each other.
Yeah.
Do you support this multi-tasking in one node?
We certainly do. It's not the way that we would recommend using the machine. If you're using it as a Eureka graph database, then you would not, in general, run other applications at the same time. We do it all the time in testing, but there isn't a good way of making sure that the other, if another application suddenly decided to grab all of the memory, you wouldn't have, I mean, the protection domains prevent you from overwriting other memory, et cetera, but someone else could use up all of the memory and therefore not leave enough memory for the database. Yeah, the protection domains are built into the ThreadStorm processor, and they've gone back to the MTA or MTA1. I think they've always been there. Yeah, the idea behind the database appliance is it's a supercomputer that is dedicated to running a single application. I mean, which appears then to the outside world as a high-performance semantic database. So it's quite possible to run other things on at the same time, but it's not really what we'd recommend. It'll certainly do it, but performance is measured by responsiveness of the database to its users on the database side. Yeah, totally legacy, yeah. Yeah.
So, correct me if I'm wrong, so the algorithm
Mm-hmm.
hashes only memory
Mm-hmm.
across the whole
Machine, yes.
machine. So it's not only that you don't need to think about locality, that you really not think about locality.
Mm-hmm.
It
Yeah.
is thinking to the machine. So you cannot say a node and run your node. Okay, you're using the CD to know like the data.
Is always everywhere.
These are things changes completely to look at this machine process.
Yeah, and so we don't have that much. We can control how many threads that you're allocated by your processor allocation, but we don't actually, there's no way of controlling where the memory will be stored or who uses it. It's first come, first serve on the memory, actually. So, okay.
That's about better.
What's that? Yeah. No, there are no data caches. We have an instruction cache. Yeah. Okay, well, maybe we can talk about this a little more when I talk about the architecture itself. So, oh, no problem. It's whenever I say it's cache-free, someone else says, well, don't you have an instruction cache? Aren't there caches in the network? But we avoid cache coherence. Anyway, we can talk about that during the architecture talk. But, oh, right, this is one of the most important parts is customer use cases. What can you use it for? So when you're looking at these, think of your own problems, and I've heard of some interesting ones out there, and see see if they match something that you might want. Now, these are customer use cases for the Eureka Big Data Appliance. Some of the things that you've already mentioned will involve programming the XMT2 directly, but both are quite possible. It just depends on how you're using the machine. In these use cases, I'll be talking about graph database use cases. Okay. I love these automated slides. Basically, this is our this is a cartoon of our simplest use case, which is basically You have data from multiple sources, which can be of multiple types. You have to import that and then connect it together in a graph, which is augmenting the relationships through inference. We have very high-speed parallel automated inference capability and ontologies that you may bring in. So you have to take all these different sources, you connect them together in a graph, and you build a large graph that contains all this data, and then analyze it, and then repeat. Keep on adding more data, keep on making more connections between it until you have a large graph that you can analyze. And then through the Sparkle language, you can search for basically patterns or templates in that large graph database that you've built. And then we also have visualization tools, and we're adding more to try to understand the data, which is actually the end use of the whole thing. You have all these different sources, graph structured data, and you want to be able to find patterns and then understand them to solve whatever problem it is that you have. So basically all of the use cases are different variations of this. Okay. Here's one of our classic Eureka use cases, which is when you're trying to find patterns of behavior that you would like to detect and stomp out. This is a intelligence scenario where when you have a large amount of fairly randomly connected data, but you have a pattern that you're looking for. This involves separate people who might live in the same house. They rent a truck. They buy fertilizer. You want to find all instances of this, and you have a huge amount of data that you've gathered from all over the place, and you want to spot this pattern. So you basically are able to hold the entire graph of your data in memory, and we have high-speed updating capability for when new data comes in. This pattern matching is really the most important feature, really, of a semantic graph database. It's a subgraph isomorphism problem. So you're basically you define a pattern that is interesting to you, and we can find it at a high rate of speed. There are many other features to the Sparkle language, but this is the core of it is this pattern matching. Of course, we have filtering, logical operations, all sorts of things, but the idea is that if you have some sort of pattern that you're interested in, it will find it. This is another customer use case. I don't know how many of you have heard of the Mayo Clinic. It's a very famous hospital in the United States. They're the proud owners of an XMT2 also. And so they're using it for healthcare analytics. And they have a large amount of data from they actually have a very large database installation, a lot of longitudinal data, historical data that spans all the events that happen to different patients. At this point, they have 10 million patients worth of patient data. And they would like to find out what patients are similar and what problems they had. So imagine you had, you'd like to find out what medicines someone was sensitive to. So you go and find all the people who have similar histories, similar symptoms, and other medications that they're taking, and see what medications have led to poor results. This is very important to them, and say it's a very large amount of data, and very complex relationships. Also, the background data used for this analysis comes from many different sources: patient records, data ontologies of drug interactions, things like that. So, and they'd also like to supply this actually to physicians wandering around the hospital with iPads, so that when they see something, they can actually query it right there. It goes back to the semantic database, and they can build patient cohorts of patients with similar symptoms. And this is something that actually is, because each query is different, This cannot be done with their relational database technology that they have now. You'd have to go to the database department and have them build up a query, and it might take weeks for the DBAs to build it for you. You might have to restructure your data, and then you get your answer. And this allows you real-time, interactive querying of this graph-structured data. So this is a very important use case, and many of other use cases will look fairly similar. Any questions? Break in if Okay. Cancer Research Institute, I guess actually I had forgotten I do have a bioinformatics use case. I'm working on this one right now with the Institute for Systems Biology in Seattle. They're basically trying to combine various data sets as part of the Cancer Genome Alliance, combining data from published literature, experimental data of theirs, and then various protein data banks. There are quite dense interconnections between this. It's not at all easily partitioned. And they're basically trying to wander around and find new relationships that have not been spotted before. The published literature on genomics is huge, and many genes are mentioned in many, many different articles. So right now for our small test graph with 10 million nodes, we have 600 million edges. So this is a very non-partitionable graph. And the other life science use cases that we've seen display similar characteristics. There aren't that many genes and proteins in the world, but there are an awful lot of relationships between them. So this is very good. When I say this is cancer, but similar patterns of query can be used for other things in the life science field. So, yes? Question? No, okay. So I mentioned earlier that though we think we're in a very important and exciting part of the database world, people will have other types of databases. People might already have Hadoop clusters, Netezza boxes, very large databases. Certainly Mayo describes this. So you have all of these other sources of big data, and then you'll want to do complex graph analytics on them. So I'll go through the workflow a little after lunch, but basically you want to import data from all of these different types of storage environments, import them into Eureka, draw conclusions from them, and if necessary, store the results in your big database. So we want to, we're not trying to take over the entire field, just the graph analytics part of it. Most important thing really about the machine is that it was designed to be very, very scalable using supercomputer technology, which actually, believe it or not, all the rest of them don't have. We're just lucky because we're Cray and we have that sort of thing. So basically, just in summary, for Eureka, basically, we'd like to discover unknown and hidden relationships. This is pattern matching that I talked about. Like to be able to perform real-time analytics on very, very large graphs in a very scalable fashion. As the size and complexity of both the queries and the database increases, we'd like to still be doing just as well. And then finally, using industry standard software layers, it allows people to interact much more easily with our machine. And also, people get very nervous because this is a proprietary architecture. So we basically like people to be able to work on any machine and just get the fastest performance on ours. So that's all I have. Are there any more questions about the Eureka Appliance? Or we'll be talking more about the XMT, of course. Yeah. What's that? Oh, no, you.
From what I know about the smart community and education management community, they always talk in terms of digitization. So probably because the relation that you showed now, that you're referring to very big data. Probably it would be also nice to show for some small databases, but to show very, very big performance with small data.
Okay. Yeah, if you have a very small database, you
very
can.
small, but just to know the size of the base.
Okay.
And the accuracy.
Yeah, these databases were the size of the entire machine's memory, so they were terabytes. I think 25K is 5 billion triples, and 100K is 20 billion triples. So they're quite large. Okay, and we did more database sizes, and I have a whole hour-long presentation on this benchmarking effort. Yeah. There's another question in back. Oh, okay. Yeah.
Someone doesn't have to not cover the whole menu with data, but maybe you just want to look at writing an application using this writing into task development time and also with execution time. Instead of control the more traditional application, you think this is the case, but you have to cover this.
Oh, it's very scalable, so it scales down as well as up. So our results are good on smaller databases also. We show the gap in performance shows off best in very large databases, and so that's why we talk about them. But the raw performance is good on small machines too. Another point in your question, I think, was how rapidly people could develop their applications. And so you can actually load Jenna onto your laptop and query it, and you can actually do your development on a very small machine if you have a database that will fit in your laptop. So when you're testing your queries or doing anything like that, all of your development can be done on any other platform, and using tools which you already own and basically or download from the web. And that's one of the big things is that if you're doing XMT C++, there's only one place you can do it. So that hopes to that was the time to solution, I guess, is the way that we talk about that. Yes. Let me see. There certainly are. There's MTGL, multi-threaded graph library. John, there was a question about what graph libraries are available. Mhm. Oh, let me see. That's something that we're working on, which is an API that will allow you to use these other graph libraries with the data that's stored in uRiKA. We do not have that capability yet. What's that? Yeah, if you are running one of those graph libraries, that's a separate application than uRiKA. So we get many requests for an interface between those two libraries and the uRiKA data store, but we have not put that in there yet. So if you use those libraries, those would be a separate standalone application. Oh, yes, yeah, it certainly. And as a matter of fact, right after lunch, I have a diagram that shows how it's stored. But right now, that's internal.
Okay. Thank you.
Thank you very much.